There are landscapes that feel like an empty page, and others that reveal their details only when you look slowly. A desert is not simply a lot of sand or a lot of heat, but a measurable imbalance between water supplied and water demanded. It is a place defined as much by what the sky refuses to deliver as by what the ground is still able to build. It is dryness written into air, soil, and stone, repeated across seasons until the pattern holds. And tonight, we'll follow the evidence gently, one calm detail at a time. Welcome to Science to Sleep To. If we haven't met, I'm Madeline Rowe, an astrophysicist turned private eye, and I keep odd hours for odd mysteries. Here, we file the world into quiet, orderly folders and let the details do the work while you rest. Tonight's folder is simple on the tab and enormous on the inside. Deserts. Not as a cliché of heat and dunes, but as a precise kind of climate, measured in balances and thresholds. Back in my office, I'm seated beside a window that holds a dark pane of sky, and the faint suggestion of distance beyond it, the kind of distance you can't rush. A small desk lamp pools warm light across my notes. A mug sits close by, sending up a thin ribbon of steam that curls and disappears, like water leaving the surface of a warm pan. On the desk, the folder waits where the light is strongest. The label is plain, almost too plain for the amount of world it contains. Deserts. Just the word, in calm block letters, as if dryness was something you could file neatly and understand by turning a few pages. I rest my hand on the cover for a moment. The paper is cool under my fingertips. Outside the window, the sky doesn't offer much movement. No obvious weather, no hurry, no commotion. Inside, everything is arranged for slow attention, because deserts are not built for rushing. They're built from long balances, from small inputs, from patient losses. And once you start reading them that way, they become less like empty space and more like evidence. And one last thing, if you'd like more calm case files like this one, you can subscribe and return whenever you need a little science and a little quiet. Alright, I'll open the folder slowly, not with drama, but with definitions, because deserts are best understood when we give them the right names. And the name desert is stricter than people think. A desert can be hot, but heat is not the rule. A desert can be cold, even bitterly cold, and still count as a desert, because the core clue is not temperature. The core clue is water, or more precisely, water balance. On the first page, there's a simple ratio written in calm, practical ink. It's called the Aridity Index, and it compares two things that matter more than any single thermometer reading. First, precipitation. That's the supply, the water that arrives from the sky, measured as rain or snow. Second, potential evapotranspiration. That's the demand, the amount of water that would leave a wet surface under the local conditions through evaporation from the ground and transpiration from plants. It's not exactly what does leave, it's what could leave if water were available to be taken. It helps to pause on that word, potential, because it's the quiet hinge of the whole definition. Potential evapotranspiration is not a measurement of how much water actually leaves the ground in a desert, because in a desert the ground is often not wet enough for that. It is a measurement of the atmosphere's appetite. It answers a slightly imaginary question. If there were water available at the surface, and if vegetation had access to it, how much would the local combination of sun, wind, temperature, and humidity be able to remove? That imaginary question is useful because it separates two different reasons a place can be dry. One reason is that the sky does not deliver much water. Another reason is that when water does arrive, the air is ready to take it away quickly. Deserts are often both, low supply and high demand. But the ratio lets us say this with calm precision. The demand term, PET, is influenced by several simple physical ideas. Sunlight brings energy. Energy powers evaporation. Warm air can hold more water vapor than cold air, so temperature matters. Wind matters because it replaces moist air near the surface with drier air from elsewhere, keeping the gradient for evaporation alive. Humidity matters because evaporation is driven by a difference between what the air has and what it could hold. If the air is already close to saturated, evaporation slows. If the air is dry, evaporation accelerates. So pH is, in a sense, the atmosphere's thirst, expressed as a depth of water. Different scientific methods estimate PET in different ways, depending on what data are available. Some approaches are energy balance based, using radiation, temperature, humidity, and wind. Some use a reference surface, like a standardized crop or grass, to make comparisons between places more consistent. Other approaches are simpler, using temperature and day length as a proxy for evaporative demand when other measurements are missing. The details of the equations aren't necessary for sleep. What matters is the concept. PET is not just about heat. It is about energy and movement and dryness in the air. You can even feel the idea in this office. The mug beside my notes sends up steam. That steam is water, leaving a liquid surface and entering the air. If the room were very dry, the steam would be eager, and the water would leave quickly. If the room were already humid, the steam would be less dramatic. The gradient would be smaller, and the rate would slow. That is PET in miniature: a surface, an atmosphere, a gradient. Before we move on, I like to linger on PET for one more page, because it explains a few desert feelings that can otherwise seem contradictory. Potential evapotranspiration is the atmosphere's capacity to remove water, and it rises when the air is sunny, warm, dry, and well mixed by wind. That means PET can be high even in a place that does not feel scorching, as long as the sun is strong and the air is dry enough to keep evaporation running. It is one reason some high deserts feel mild in the shade and yet still behave, hydrologically, like deserts. The air can quietly take water away even when your skin isn't complaining. It also helps explain why deserts often cool so sharply after sunset. When skies are clear, the ground loses heat efficiently by radiation. In humid places, water vapor and clouds absorb and re-emit some of that heat back downward, like a thin blanket. In many deserts, the air holds less water vapor, and clouds are often scarce, so that blanket is thinner. The surface cools quickly, and the air right above the ground cools too. Sometimes that creates a stable layer close to the surface, where colder, denser air hugs the ground and resists mixing. That is a temperature inversion, and it can make the night air feel surprisingly still, even when winds are stronger higher up. The desert can feel quiet, not because the world has stopped moving, but because the lowest layer has become calm and layered. And occasionally, in that cooled near-surface layer, the air temperature approaches the dew point. If that happens, a very small amount of water can condense as dew on rocks, plants, and any surface that radiates heat well. In some deserts, dew is rare. In others, it is a subtle but regular input, a thin film that evaporates again soon after sunrise. It does not change the annual accounting very much, but for certain organisms, a thin film can be enough to matter. So PET is not just a number on a chart. It is the reason a wet footprint can disappear quickly. It is the reason damp soil turns dry in hours. It is the reason a desert can feel cold at night and still be, in the strict accounting sense, deeply water limited. Now, once you have P over PET in your mind, deserts become less mysterious. A place can be cold and still be a desert if precipitation is extremely low. Cold air can hold less water vapour, so PET can be lower in cold regions, but if P is lower still, the ratio remains small. It can help to make that idea a little more concrete, because cold desert sounds like a contradiction until you picture what the definition is actually measuring. In very cold environments, the air's capacity to hold water vapour is limited, so you might expect that dryness would not be an issue. But the definition is not asking, is the air thirsty in an absolute sense? It's asking, does the landscape receive enough water over time to meet even that reduced demand? If precipitation is extremely low, the ratio can still be small. Some high plateaus and interior basins are dry because moisture sources are far away, and mountains intercept what little moist air tries to enter. Some polar regions are dry because the cold atmosphere contains little moisture, and the hydrologic cycle is subdued. Snow can fall, but total precipitation can still be very low year after year. And when snow does persist, it can remain locked up as ice for long spans, not readily available to plants or soils as liquid water. So cold desert becomes a calm, logical label, not a place that feels like sand at noon, but a place where the long-term water budget stays in deficit. And if you keep the ratio in mind, it makes sense that deserts can be defined in the same way across very different thermal worlds. The arithmetic does not care whether your breath fogs. It cares whether water arrives often enough and stays long enough to support a more continuous, less pulse-driven ecology. This is why we can speak calmly of cold deserts. High plateaus, rain shadow basins, deep continental interiors, and even polar regions can qualify in the same quantitative way. The stereotype of deserts as hot is a cultural image, not a scientific definition. On the next page of the folder, there are typical threshold values that researchers use to classify drylands. They are not magic numbers, but they are useful conventions. When P divided by PET drops below about 0.20, we are in the arid and hyper-arid range often associated with true deserts. Below about 0.05, the term hyper-arid is commonly used, places where rain is so rare that it can feel like an exception, and biological activity is pushed into narrow windows. Between about 0.05 and 0.20, the term arid is commonly used, still strongly water limited, still defined by scarcity, but with more frequent pulses. Beyond that, as the ratio rises, we move into semi-arid and dry subhumid zones, still shaped by water limitation, but not as extreme. This classification is one reason desert science feels orderly. It gives you a scale. It gives you categories. It lets you compare the Sahara with the Great Basin, the Atacama with parts of Central Asia, without forcing you to pretend they look the same. They do not look the same. They simply share a balance condition, a shared dryness expressed as a ratio. And because deserts are defined by a ratio, deserts can shift. If precipitation patterns change, P changes. If temperature, wind, humidity, or radiation patterns change, PET changes. And the boundary between categories can move. That movement can be slow on a human timescale, or visible over decades in some regions. But the definition stays calm and stable. It is not a vibe. It is a budget. With that in mind, we can return to the broad mechanisms that create deserts in the first place, because the same ratio can arise from different atmospheric stories. Some deserts sit under belts of descending air, where global circulation tends to suppress clouds. Some sit behind mountain ranges, where rising air drops moisture on the windward side and leaves the leeward side dry. Some sit deep in continents, far from moisture sources. Some sit along coasts with cold, upwelling waters that cool the air near the surface and make it stable, reluctant to rise into rain-producing clouds. Different stories, same ratio. Different geography, same balance. If you look at a globe, there is a calm symmetry to many of these patterns. Around the subtropics, there are belts where air that rose near the equator descends. Descending air warms as it compresses, and warm air can hold more water vapor, so relative humidity tends to drop. Clouds are less likely. Rain is less likely. The result is a broad tendency toward aridity at certain latitudes, but deserts also form in more local ways. Mountains can create rain shadows. Moist air rises over a range, cools, drops its water, and then descends on the other side drier and warmer. The leeward side receives less precipitation. The balance shifts. Continental interiors can be far from ocean sources of moisture. Storms lose water as they travel. By the time air masses reach the deep interior, the supply can be limited, and the pattern can tip toward dryness. And along some western coasts, cold ocean currents and upwelling bring cold water to the surface. That cold water cools the air above it and makes the lower atmosphere stable. A stable atmosphere is not eager to rise and build rain clouds. Evaporation from the sea is reduced. Rainfall becomes very low. And yet, paradoxically, fog can become frequent because cool air near the surface can condense water vapor into low clouds that don't lift into storms. These are coastal fog deserts. Fog deserts deserve an extra page in the folder because they remind us that water from the sky can arrive in more than one form. Along certain coasts, cold currents and upwelling keep the surface air cool. Cool air near the surface tends to be stable, and stable air does not rise easily into tall storm clouds. Instead, moisture can condense into a low marine layer, a sheet of stratus or fog that slides inland at night or in the early morning and then retreats. The droplets in fog are tiny, and many of them never fall as measurable rain, but they can still deliver water to the surface in quiet ways. When fog brushes against vegetation, droplets can collide with leaves and spines and drip downward. When fog meets rough rock or gravel, droplets can collect and coalesce, wetting the topmost grains. This kind of delivery is sometimes called occult precipitation, not because it's mysterious, but because it's easy to miss on a rain gauge. In some fog deserts, this thin input supports narrow bands of life. Lichens can grow on stones, where fog is frequent. Some plants have surface textures that help catch droplets. Some animals time their activity to the hours when fog is thickest, taking advantage of cooler temperatures and the presence of moisture on surfaces. It is not a substitute for rain, and it usually does not recharge groundwater deeply, but it can be enough to support life on the margin. It's a reminder that the desert's definition is not nothing arrives, but the accounting stays negative. Some of the driest ecosystems on Earth sit in places where you can hear waves. The Namib is a classic example. The Atacama is another. They teach a gentle lesson. Dry does not mean no water in any form. It means the water budget is negative. It means the delivery mode is limited. It means rain is rare. But fog can still arrive as a thin gift, and certain organisms can learn to catch it. Now, deserts are often described as empty, but the folder insists on the opposite. Deserts are structured. They are not just a lack of water. They are systems with characteristic landforms, soils, and ecological strategies. So we turn another page. This one is about the ground. In many wetter environments, chemical weathering is strong. Water moves through soils, dissolves minerals, carries them away, and supports thick vegetation that adds organic matter. In many deserts, chemical weathering is weaker, not absent, but slower because water is less available. Physical weathering can be prominent. Temperature swings can stress rock. Salt crystals can grow in pores and push grains apart. Occasional wetting and drying can fracture clay-rich surfaces. Wind can abrade. Water can flash through channels and move sediment in bursts. The desert ground is therefore often a mosaic: rock outcrops, gravel plains, sand sheets, dune fields, alluvial fans, dry lake beds. There's one more kind of desert evidence that doesn't require a flood or a dune field to notice it. It sits on rock surfaces, quietly, like a stain that takes a long time to appear. In many deserts, exposed stones develop a dark coating, often called desert varnish. It can be patchy or continuous, glossy or dull, and it tends to form on stable surfaces that have remained exposed for long periods. The exact chemistry and formation pathways can vary from place to place, but the basic idea is steady. Extremely thin layers can accumulate over time, influenced by dust deposition, trace minerals, and slow surface processes. Researchers still debate the relative roles of dust, chemistry, and microbes in how varnish builds, but the slow timescale signal is consistent. It is not a fast record. It is a patience record. And because it forms slowly, varnish can sometimes hint at surface stability, at how long a rock face has been exposed to open air and open sky. Alongside varnish, deserts also produce their own style of physical weathering, often driven by salts. When water briefly wets a rock through a small rain or fog or dew, it can carry dissolved salts into tiny pores and cracks. Later, as the water evaporates, those salts can crystallize. Crystals take up space, and that expansion can exert pressure on pore walls, gradually prying grains apart. Over long periods, repeated cycles of wetting, evaporation, and crystallization can break down rock surfaces without the need for constant flowing water. Temperature swings can contribute too. A sunlit rock can heat strongly by day and cool rapidly at night, especially under clear skies. Different minerals expand and contract at different rates, and repeated stress can exploit existing fractures. So even in a dry climate, rock can still be worked. Not through lush chemical dissolution, but through repetition, thresholds, and small cycles. The desert, in this sense, is not a place where weathering stops. It's a place where weathering chooses different tools. And when you learn to recognize those tools, thin varnish, salt-fractured edges, wind-smoothed faces, the desert's surface begins to read like a document instead of an emptiness. And once you notice those slow surface records, it becomes easier to notice the bigger patterns too. Not all deserts are sandy. In fact, many deserts have relatively little sand at the surface. Sand is one size class, a particular fraction of sediment. Many deserts are dominated by gravel and stone, especially where wind has removed fine material and left an armoured surface. In the folder, there is a quiet note about this. The common mental image of endless dunes is only one desert type among many. It is memorable, and so it dominates imagination. But the science is broader. Now we move to the major sculptors: Wind and episodic water. Wind is often continuous in deserts, not always strong, but frequent. It can lift fine particles. It can move sand. It can polish rocks. It can strip the surface. Water is often infrequent, but when it arrives, it can be intense. A single storm can produce floods. It can cut channels. It can transport boulders. It can spread sediment into fans. The desert is therefore shaped by two rhythms, a steady rhythm of wind and a pulsed rhythm of water. To keep it calm, we don't need to imagine disaster. We can imagine a simple basin, a mountain range at the edge, a broad slope of debris at the base, a flat basin floor, a rare storm. Water runs down the mountain. It reaches the slope at the base. It spreads. It drops sediment. Then it disappears. Over many events, this builds an alluvial fan. Fans can overlap and form a bahada, a broad apron of coalesced fans along a mountain front. The basin floor can collect the finest material. If the basin is closed, meaning it has no outlet to the sea, water that reaches the lowest point can form a playa or salt flat. It evaporates, leaving minerals behind. This is one of the most orderly patterns in desert geomorphology. High to low, coarse to fine, rock to gravel to sand to silt and clay. And at the lowest point, often salt. Even if a wash runs only a few times each year, it can transport enormous sediment when it does. And over centuries, that becomes a fan. Over millennia, a bahada. Over longer spans, a basin filled with layered deposits. If you look at a desert basin from above, you can often read it as a gradient. Coarse debris near the mountain front, finer sediment farther out, and the finest with salts at the lowest point. It's a calm sorting machine. Gravity helps, water helps when it arrives, wind helps in the spaces between. If you could take that basin and slice it like a layer cake, you would see another quiet pattern. In wetter landscapes, coarse soils often grade into finer soils upslope because water carries fine particles downhill and leaches them deeper. In many deserts, the pattern can feel inverted. The hill slopes are rocky. The foothills can be stony. The alluvial fans and bahadas are often sandier, a mix of sand and loam laid down by energetic flows, leaving the mountains. And the valley bottom collects the finest materials, silts and clays, because those are the particles that stay suspended longest in muddy water and settle only when the flow slows to stillness. That fine valley bottom material is one reason playas can be so flat and so smooth. Clay seals the surface. It becomes a temporary skin. After a storm, water can spread thinly across it, reflecting the sky for a few hours or a few days. Then the water is gone. The surface dries, cracks open, and the basin returns to quiet. Each wetting and drying cycle leaves a trace. Some traces are physical, thin laminae of silt and clay, stacked like pages. Some traces are chemical, dissolved minerals left behind as crusts. In deserts, because rain is infrequent, the usual leaching that carries dissolved material downward is weak. Evaporation often dominates instead, pulling moisture upward through capillary movement. As that moisture rises and escapes into the air, it leaves minerals closer to the surface. Over long time, this can build distinct horizons. Calcium carbonate accumulation, gypsum accumulation, silica-cemented hard pans, and salt crusts in the most closed and evaporative settings. These crusts are not merely geological curiosities. They change infiltration. They change how roots explore the soil. They can make a surface more resistant to erosion or more prone to runoff, depending on texture and structure. And they connect directly to plant life, because salts affect water uptake. Dissolved ions lower the water potential of the soil, so a plant must work harder, in a physiological sense, to draw water in. Certain ions can also interfere with nutrient balance, so vegetation, when it can exist near a salty basin, tends to be specialised. Salt-tolerant plants can fringe the salt flat. Less tolerant plants stand slightly higher where the salt concentration is lower. And farther up the fan, where infiltration is easier and salts are less concentrated, you can find a different suite of shrubs and grasses. There is a quiet elegance to that arrangement. It can look, from a distance, like someone painted rings and gradients onto the land. But it is simply the water budget at work, sorting particles and concentrating minerals with calm persistence. And beneath that surface, there is one more gentle truth. Soil is not dead dirt. Even in deserts, soil is a living skin. It is the surface that partitions rare rainfall into runoff, into water held briefly in pores where plants can reach it, and into occasional drainage that feeds groundwater. It is shelter for microbes. It is a storehouse for seeds. And it is a record of time because a soil profile is a history written downward, from the surface to deeper layers. In deserts, that history is often slow and subtle, but it is still there, waiting to be read. Now, because this is Deserts for Sleep, we take a moment to slow even further and look at the most basic thing deserts do to a person's perception. Deserts change your sense of scale. They simplify the view, not because they are simple systems, but because they often have fewer tall, complex vertical structures than forests or cities. The horizon can be more continuous. The sky can feel larger. The distance can feel cleaner. That perception can be calming. It can also be misleading, because deserts are not empty. They are just quieter in certain dimensions. If you were walking in a desert, you might notice that sound carries differently. Wind over gravel, a dry leaf clicking, a distant bird. The silence is not absolute. It's just less crowded. In the office, I let that idea sit for a moment. A wide horizon, a sparse set of objects, a clean line between ground and sky. And then I return to the folder, because deserts have more evidence to offer. The next pages are about life. Deserts are water-limited systems. That is the rule. But life finds ways to fit itself into the rule. The simplest strategy is timing. Many desert organisms do not try to be active all the time. They wait, they pulse. Plants can wait as seeds, sometimes for years, until a rain event triggers germination. Then they grow quickly, flower quickly, set seed, and return to waiting. This is a strategy for a world where the mean rainfall is less informative than the timing of rainfall. Other plants invest in structure, deep roots, storage tissues, thick cuticles, reduced leaves, spines. These are strategies for persistence, for surviving long dry stretches. Some plants shift their photosynthesis. Instead of opening stomata during the day, when heat and dryness would drive high water loss, they open stomata at night, when the air is cooler and humidity is slightly higher. They take in carbon dioxide at night, store it, and then use it during the day. This strategy reduces water loss. It is one of the famous tools in the desert plant toolbox. In many deserts, biological soil crusts form on the surface. These are communities of microbes, lichens, and small organisms that bind soil particles together. They can reduce erosion, they can influence infiltration, they can contribute to nutrient cycles. They are another reminder that even bare-looking ground can be alive. That living skin deserves a closer look, because it is one of the most important structures in many deserts, and one of the easiest to overlook. Biological soil crusts can include cyanobacteria, bacteria, algae, fungi, lichens and mosses, bound together with mineral grains at the surface. Some organisms form filaments that weave through sand and silt, creating a mesh. Some produce sticky substances that help glue particles together. Over time, the crust becomes a thin layer that changes how the surface behaves. When the crust is dry, it can look like almost nothing at all. A faint darkening, a slight roughness, a brittle skin. But when it is wetted by rain, dew, or fog, it can wake quickly. Photosynthesis can switch on. Nutrient cycling can accelerate. In some crust communities, nitrogen fixation becomes possible, adding a limiting nutrient to soils where organic inputs are otherwise sparse. Then, as the surface dries again, activity slows, and the organisms return to dormancy. These crusts matter for physics as well as biology. A crusted surface can resist wind erosion, reducing the amount of dust that can be lifted. It can change infiltration, sometimes increasing it by stabilizing pore structure, sometimes decreasing it by forming a seal, depending on crust type and soil texture. It can also create small, stable microhabitats where seeds and seedlings have a slightly better chance. So deserts can be both resilient and fragile at once. Resilient because life has ways to pause and restart. Fragile because a thin living layer that took years to develop can be broken quickly by repeated disturbance, and above that quiet surface layer, other forms of life keep their own schedules. Animals have their own strategies. Many desert animals are nocturnal. They avoid the hottest part of the day. They burrow, they shelter in shade. They reduce water loss. Some obtain much of their water from food and metabolic processes. Some are adapted to tolerate dehydration better than many animals from wetter environments. And desert animals, like desert plants, often rely on behavior rather than constant physiology. Move to shade. Become inactive during heat. Become active when conditions are kinder. In deserts, behavior is often the first line of adaptation. Now, the folder has a section on pulse dynamics, and it's one of the most comforting sections because it explains why deserts can look static and yet be full of life. In deserts, productivity often comes in pulses after rain. Microbes respond. Plants respond. Insects emerge. Animals become active. The system wakes up, then gradually quiets again as moisture is lost. This is not a failure, it is a rhythm. It is the desert's normal tempo. You can think of it like a lamp that is not always on, but that still defines a room. The pulses matter. They shape species. They shape soils. They shape landforms. But they do not need to be frequent to be significant. The folder also reminds me that deserts are not all the same in their biological patterns. Hot deserts and cold deserts differ. Fog deserts differ. High elevation deserts differ. Some deserts have winter rains, some have summer monsoons. The seasonality of precipitation changes everything. In some deserts, winter storms are the main supply. In others, summer convective storms dominate. In still others, both are small, and fog or dew may matter. So the desert is not one place. It is a category of balance states, expressed in different climates. Now the folder returns to wind again, because wind is such a persistent force in arid landscapes. Wind can remove fine particles and leave a coarser surface. This can create desert pavements. It can create stony plains. It can create surfaces that resist further erosion because they are armoured. Wind can also create dunes where sand is available. Dunes are storage systems for sand. They hold sediment until a shift in wind regime or vegetation or human disturbance changes the pattern. Dunes can be active, moving, reshaping, migrating, or they can be stabilised by vegetation or moisture or crusts. A stabilised dune is not dead. It is simply in a different state. In some deserts, dunes form huge fields called ergs or sand seas. From above, they look like oceans, but they are oceans of grains. They store the history of wind. In the folder, there is a note about how wind and water can interact. Water can supply sediment that wind later reworks. A flood deposits sand. The surface dries. Wind picks it up. Over time, water can be the supplier, and wind can be the sculptor. Now, there is another page about desert rivers, and it is worth turning slowly because it's a common misunderstanding that deserts have no watercourses. Deserts often have ephemeral channels, wadis, arroyos, dry washes. These channels may be dry most of the time, but they matter because they concentrate flow when rain occurs. A wash can carry water for minutes or hours after a storm, then go dry again. But over time, it can calve, it can build, it can transport sediment downstream, it can recharge groundwater where infiltration occurs. So again, deserts are not places where nothing happens. They are places where the timing is different. The folder includes a quiet caution that floodplains exist in deserts too, even if they look dry most of the year. And that is not meant to create alarm. It is meant to emphasize the scientific point. A dry channel is still a channel. It is still part of a hydrologic network, waiting for the pulse. Now, as the pages continue, we come to a chapter that many people find surprising. Deserts can be important archives. Dryness can preserve things. Organic materials that would decay quickly in humid environments can persist longer. Landforms can remain recognizable. Ancient shorelines of paleo lakes can be traced in basin margins. Dune deposits can record wind patterns. Soil layers can preserve evidence of past climates. This is how scientists reconstruct desert history. They read the landscape. They read sediment layers. They read minerals and isotopes. They read fossils when available. They read the desert as a file of past conditions. And the desert file often shows that deserts have not been constant. Many deserts have expanded and contracted with climate cycles. During wetter periods, lakes formed in basins that are now dry. Vegetation patterns shifted. Dunes stabilized or reactivated. Rivers flowed differently. So the desert is not a permanent absence. It is a climate state that can persist for long periods, but it can also change with global patterns. There's one more definition page I like to keep in this folder, mostly to keep the language tidy. Drylands is the broad category, usually defined by aridity index ranges that include semi-arid and dry subhumid regions, as well as arid zones. Deserts, in many strict uses, refer to the more extreme arid and hyper-arid end of that spectrum. The exact thresholds can vary slightly by source, but the structure of the idea stays the same. Drylands are the family. Deserts are the most water-limited members of that family. And then there is the word desertification, which is easy to misunderstand if it's not filed correctly. Desertification does not mean deserts are unnatural, or that a desert appearing is automatically a mistake in nature. Deserts can be stable, ancient biomes, and many have been part of Earth's system for very long spans of time. Desertification is a different label. It usually refers to land degradation in dry land regions, where soils, vegetation, and productivity decline due to a combination of pressures that can include climate variability and human land use. It can show up as increased erosion by wind and water, reductions in plant cover, changes in soil structure, and in some settings, increasing salinity where water and salts are managed poorly. This page isn't here to add drama, it's here to keep the case file precise. A desert can be a normal climate state. Desertification is a process that can occur within drylands, and the distinction matters because it keeps our definitions honest. And once the terms are separated like that, the rest of the folder reads more calmly. We can talk about deserts as systems and about change as change, without mixing the two into a single vague word. Now, the folder has an especially calming point, because it reduces everything again to a few core variables. Deserts are about water balance. Water balance depends on the atmosphere, the ground, and the timing of storms. The atmosphere provides precipitation and sets evaporative demand. The ground controls infiltration, runoff, storage, and salinity. Timing determines pulses. If you hold those three ideas, you can understand desert science in a restful way. Now, we slow again, because a good case file, even a scientific one, doesn't need to be rushed. We can let the mind drift through a few more details, like turning pages without needing to memorize anything. Consider the atmosphere over a desert on a clear day. The air is often dry. The sky can be a deep, uninterrupted blue because water vapor is a greenhouse gas and also a scatterer, and when it's reduced, the visual texture changes. Haze can still occur, especially in dusty conditions, but it has a different character than humid haze. It can look like distance made visible. Consider the way wind moves across the surface. Wind does not carry all grains equally, and that unequal carrying is one of the quiet engines of desert form. The air itself is a fluid, turbulent and restless, and near the ground it behaves like a hand that can only lift certain weights. The smallest particles, the silts and clays, can be held aloft as dust. Once they are in suspension, they can travel far, crossing basins, crossing seas, sometimes crossing oceans. They tint the horizon. They make a thin veil of haze. They can turn a sunset softer or sharpen it, depending on what is in the air. And when they finally settle, they do not always settle back into the same desert. A portion of a desert can become, quite literally, airborne. A desert participates in global cycles by exporting its finest grains. Sand behaves differently. Sand is usually too heavy to stay in suspension for long. Instead, it moves in a hopping, skipping motion called saltation. Grain by grain, the surface becomes a little percussion instrument. A wind gust lifts a sand grain a short distance. The grain lands. The impact knocks loose other grains. Some hop, some roll, some creep forward in tiny nudges along the ground. Saltating grains rarely rise very high. Much of the action stays within a metre or so of the surface, concentrated in the lowest layer of air, where the wind is slowed by friction, but still strong enough to do work. If you've ever watched wind move sand in a low, shimmering sheet, you've seen a boundary layer made visible. This is how ripples form. A sand surface under steady wind is not content to stay flat. It organises into crests and troughs, small repeating ridges whose long axes tend to lie perpendicular to the wind direction. The spacing between ripples reflects the typical length of a saltation hop, like a measurement you can see. In ripples, the coarser grains tend to collect at the crests, making the ridgeline slightly rougher than the trough. And over longer times, as sand continues to accumulate, the repeating pattern can scale upward into dunes. A dune is not just a pile, it is a moving record. It has a gentle windward slope where grains climb by hopping and creeping, and it often has a steeper leeward slope, the slip face, where grains avalanche when they reach the angle of repose. The avalanching is small and frequent, like quiet sandfall, and it rebuilds the same slope over and over. That repetitive rebuilding is why dunes can look so clean in profile. Flow becomes form. Form becomes a kind of memory of flow. Different wind histories build different dune geometries. Crescent-shaped Bartian dunes form where sand supply is limited and wind direction is relatively consistent. They can migrate noticeably over time, sometimes meters per year in active settings, moving like slow creatures across a flat surface. Long linear dunes can form where winds converge or where there is a dominant direction with secondary winds, creating parallel ridges that can run for long distances. Transverse dunes build ridges perpendicular to a prevailing wind, where sand is abundant and vegetation is sparse, sometimes joining into wide fields that look like waves frozen into land. Parabolic dunes, with their arms pointing upwind, often involve some anchoring by vegetation, a reminder that biology can tug on geomorphology even in dry places. And star dunes, with radiating arms, can form where wind direction varies, building multi-armed hills that may stay in place for long periods, like landmarks that the wind itself has agreed not to erase quickly. Not all wind-blown sand becomes dunes. Some deserts hold broad sand sheets, gently undulating surfaces where the grains are too coarse, or the wind regime too variable to build tall dunes everywhere. These sand sheets can cover large areas and can be, in their own way, just as informative. They tell you there is a supply of sand, a persistent wind, and time. They tell you the surface has been worked. And then there are surfaces where wind does not build, but removes. In some broad desert plains, repeated removal of fine material leaves behind an armoured layer of stones, a desert pavement. It can look arranged like a mosaic, but it is simply what remains after winnowing. It is a surface that resists further erosion precisely because it is coarse. A self-protecting skin. Wind can also erode by abrasion, a kind of natural sandblasting. Sand grains driven by gusts strike exposed rock. Over time, they polish, pit, and shape it. Stones can become ventifacts, carved on one or more faces by persistent abrasion. In softer sediments, wind can sculpt larger streamlined ridges called yardangs, elongated forms aligned with prevailing wind direction, as if the landscape has been combed. Even here, the story is not dramatic. It is patient. It is repetition. Now, because deserts are so often associated with dust, we can return to that suspended fraction for a longer, gentler look. Most dust emission does not happen because the wind simply lifts clay and silts straight up. It often happens because wind first sets sand grains into motion. Those saltating grains strike the surface like tiny hammers, dislodging finer particles. Once the fine particles are freed, turbulence can carry them into the air, where they can remain suspended for hours or days. Sand is the mover, and dust is the passenger. There is a threshold to this process. Below a certain wind stress, grains stay put. Above it, motion begins, and emission can rise quickly. That is why dust storms can feel sudden, like a curtain pulled across a landscape. Not because the world changed instantly, but because the system crossed a boundary. Deserts have several ways to cross that boundary. Strong winds behind fronts, downburst winds from thunderstorms that spread outward as dense, fast-moving air, small rotating columns driven by surface heating that lift dust locally. In some places, a wall of dust can roll ahead of a storm, carried by the storm's own outflow. And once dust is airborne, the desert becomes less local. A portion of the landscape becomes atmosphere, and the evidence travels. Dust is not just a nuisance, Dust is a transport mechanism. When fine particles leave a desert, they carry minerals with them. They can deliver nutrients to faraway soils. They can deliver iron to parts of the ocean where iron is scarce, subtly influencing marine productivity. They can provide tiny surfaces on which water vapour can condense, influencing cloud microphysics. They can absorb and scatter sunlight, altering how radiation is distributed in the atmosphere. Sometimes dust cools the surface by reflecting sunlight. Sometimes it warms the air aloft by absorbing it. The net effect depends on particle size, composition, and how dust is layered. This is one reason deserts are never fully isolated. They breathe material into the planet's circulation. Now consider the way water moves when it does arrive. In many deserts, rain comes in pulses, and the land responds quickly. Some surfaces, especially those with fine textures or crusts, shed water at first, producing runoff within minutes. Other surfaces, especially those with roughness or vegetation cover, take water in more readily, increasing infiltration. So deserts develop a patchwork of sources and sinks. A stony slope may shed water. A low swale may receive it. A channel may gather it. A small basin may hold it briefly. A shrub can concentrate water at its base through stem flow, creating a small wetting pattern under and around the plant that is larger than the plant itself. In deserts, spatial patterns of water matter because the input is scarce and uneven. After a rain event, the clock starts. Some water is lost quickly to evaporation from the surface. Some is taken up by plants, some drains deeper. But the characteristic fact in many deserts is that the depth of wetting from common rains is not very great, often not greater than the rooting depth of the plants adapted to that regime. Below that, soils can remain permanently dry. Deep recharge to groundwater tends to be limited and episodic, occurring most effectively where water is concentrated, in channels, in run-on areas, and sometimes in coarse, deep wetting soils such as dunes, where infiltration can be rapid and evaporation from depth is slower. This is where the desert basin becomes relevant again. Mountains, when they receive rain or snow, discharge runoff onto alluvial fans. Those fans can overlap into bahadas, broad aprons that grade toward the basin floor. And because bahadas and large alluvial fans can store water in their sediments, they can be important sources of groundwater. Down in the lowest parts of a closed basin, water that arrives has nowhere to flow onward. It pools in playas or ephemeral lakes. It evaporates, and the dissolved minerals that water carried are left behind, accumulating over time. So we arrive, naturally, at salts and soils. Because rain is rare, leaching is weak, and evaporation is strong enough to drive capillary movement upward, pulling dissolved salts toward the surface. This can create crusts, carbonate crusts, gypsum crusts, salt crusts. In some soil classifications, there are specific names for these tendencies. Soils where soluble salts accumulate in closed depressions. Soils where sodium-rich chemistry shapes structure. Soils where gypsum or calcium carbonate build distinct horizons. Even hard pans. The technical names are less important tonight than the simple mechanism. Water arrives with minerals. Water leaves as vapour. Minerals stay. Over repeated cycles, the surface becomes a ledger of what has been delivered and concentrated. Those salts matter to living things. They can intensify drought stress because dissolved ions lower the water potential of the soil, making it harder for plants to take up water. Certain ions like sodium can interfere with nutrient uptake, so the vegetation near salt flats can become specialised. Halophytes, salt-tolerant plants, often form belts around playas, marking the boundary where salts are most concentrated. If you ever see a ring of distinctive vegetation around a bright basin, you are seeing chemistry expressed as ecology. And now, because deserts are not only physics and chemistry, but also people, the folder offers a calm aside about oases. An oasis is not magic. It is hydrogeology and engineering and time. Some oases are fed by springs, some by streams led into channels, some by groundwater lifted from wells. And in many desert regions, people have developed systems that harvest groundwater from alluvial fans and mountain basins and bring it gently to the surface. There are tunnel and well systems, known by different names in different regions, that tap deep water and deliver it downslope along a small gradient. On the surface, these systems are marked by a line of openings, like a dotted line drawn across the desert. The physics is quiet. Gravity, permeability, a gradient. And the result can be shade, trees, crops, and a small pocket of sustained moisture. Now we can return to organisms again, with the sense that the setting has become richer rather than noisier. Plants respond to desert constraints with strategies. Some are built for patience, deep roots, slow growth, long-lived tissues. Some are built for speed, seeds that wait through dry years and then burst into growth after rain. Some store water, some reduce water loss with thick cuticles, small leaves, or spines. Some shift their gas exchange into the night, using a form of photosynthesis that opens stomata when the air is cooler and humidity is slightly higher, reducing water loss. And in deserts, timing is a trait. Knowing when to act can be as important as having a particular form. Animals respond too, often by rearranging their day. Many desert animals are nocturnal. They burrow. They rest in shade. They use behavior to manage heat, moving between sun and shadow like a careful thermostat. Some conserve water by producing concentrated urine, dry feces, or by relying on metabolic water produced during the breakdown of food. Some exploit brief wet periods and then retreat, and many animals, from insects to mammals, use the same quiet logic: avoid exposure, reduce losses, and match activity to the right window. Nocturnality, burrowing, water conservation physiology, behavioral thermoregulation, tracking resource patches is part of the same logic. In a pulse-driven environment, mobility and timing can be as important as strength. And in some deserts, the pulse doesn't arrive as rain at all. It arrives as fog or dew, thin enough to miss on a gauge, but real enough to support life at the margins. We've already filed that evidence earlier in the folder, and it fits here too, as one more way deserts turn scarce water into usable timing. Now the folder offers one more layer, and it's a layer that often surprises people. Deserts can be ancient. Some dune systems and desert landscapes have persisted for millions of years, shifting and reworking, but remaining within a desert regime long enough to accumulate thick sedimentary records. In the Namib, for example, geological evidence suggests long-lasting arid or semi-arid conditions over long spans of time, with major dune accumulations recorded in sedimentary formations. Other deserts are younger in their modern configuration. Climate shifts can create and remove deserts in geologic terms fairly quickly, and so deserts exist on a range of timescales, from very old desert landscapes with long records to more recently established arid zones. This matters because it shapes evolution. If a desert persists for long periods, organisms can specialize. If a desert is intermittent over history, organisms may carry traits suited to dryness, but remain flexible. Now we return to the human scale, because that's where you are tonight, listening in a quiet room, and the case file is meant to be restful. At the human scale, deserts can feel like pure space. but the science tells a different story. Deserts are not empty. They are structured by water deficit, shaped by wind and episodic water, and animated by pulses. Even a simple desert walk contains many microclimates, shade under a rock, a north-facing slope versus a south-facing slope, a channel that collects runoff, a patch of soil with a crust, a patch without, a small plant creating a tiny zone of higher humidity near the ground, a burrow holding stable temperature and moisture. Deserts are full of small gradients. And those gradients matter because in a limiting environment, small differences can determine survival. If you want to let your mind drift with an image, imagine the desert as a map made of faint, overlapping layers. A climate layer, a topography layer, a soil layer, a vegetation layer, a hydrology layer. Each layer is sparse, but together they make a coherent system. Now, as we near the end of the folder, there is usually a page titled something like variability or uncertainty, because deserts are not only dry, they are often unpredictable. In deserts, rainfall can vary a great deal from year to year. Some years may bring a sequence of storms. Other years may bring almost none. The mean can be misleading. The timing is everything. This is one reason deserts are often described as environments of extremes, not only in temperature, but in variability. But again, we don't need to dramatise. We can simply say that the statistical distribution of rainfall is often skewed. Long dry gaps, occasional big events, and organisms and landforms reflect that distribution. This brings us back to large-scale drivers, but now we can hold them in a softer way. The jet stream can shift, storm tracks can change, polar front boundaries can move, monsoon intensity can rise and fall. ENSO events can tilt patterns across continents. The Pacific decadal oscillation can modulate the background state over longer periods. And these drivers can change the probability that a desert receives its next pulse. Sometimes, when people talk about deserts, they talk as if deserts are simply places where nothing happens. But the truth is that deserts are places where the timing of happening is different, and the causes of that timing can be global. If you've stayed awake through this, you've done more than enough. You can let the remaining words blur into a kind of steady, factual lullaby. Because deserts, once you understand their definition, become simple in a calming way. Supply versus demand. P over P, E, T. A ratio, a threshold, a classification, a stable belt of descending air, a cold upwelling coast, a mountain shadow, a far interior, wind-sorting sediment, floods building fans, players collecting salts, rain pulses waking life, global drivers shaping when pulses arrive. That is the full case, and it closes neatly. I'll take a moment to straighten the pages in the folder, not because they're messy, but because the ritual of order is part of the calm. Definitions first, mechanisms next, landforms after that, ecology, variability, recap. And now, to end the file, we can return to the simplest and quietest sentence in the whole investigation. A desert is a place where the long-term water balance is negative. You don't need to remember the ratio, or the thresholds, or the classification terms. You can simply let the idea sit in the mind like a smooth stone. Supply and demand, a calm mismatch, a landscape shaped by that mismatch. And if you're ready to sleep, you can let that thought become softer. Let it drift. Let it dissolve. Outside the office window, the sky doesn't change much. Inside, the lamplight stays warm. The folder lies open, but it no longer needs to be read. The definitions have done their work. I'll close the folder gently, not like a conclusion, more like a soft cover placed over a page you can return to anytime. And if you're ready to sleep, you can let the deserts of the world become what they often are from far away. A pale band on a map, a calm space between wetter places, a reminder that Earth has many ways of balancing itself, even when the balance looks like absence. Good night.